All right, so today, my friends, we are talking about inequalities in one triangle. So yes, going back to greater than, less than, all of those fun things that we talked about in algebra, but we're going to apply it obviously to the base of good old-fashioned geometry. But really what we're doing now is still talking about positions and stuff, describing triangles well. Because remember, chapter 5 is that chapter where they put all the different stuff for triangles in one chapter and say, hey, this is what you need to learn. Also remember, we only go through section 6 this semester. I actually pull section 7 and 8 later in this next semester, and you'll see why it just flows better in the then and instead of now. So we're going to talk about this, but guys, I want you to think about common sense stuff with me and remember a few things that we've talked about in our past. First of all, if I talk about triangle ABC, we have to talk about opposite sides and opposite angles, right? Angle B is opposite what side? Which one is it? Yeah, AC. Excellent. What is segment BC opposite of? Angle A. Now here's my question. What if I made angle A smaller? What if I made angle A smaller? What happened to segment BC? It got what? It got smaller, right? So what if I made angle A really big? What happened to segment BC? Did it get bigger, longer too? Like, so doesn't the opposite angle affect the opposite side measurement? Now, you guys have already talked about this in your life. I want you to know that. How many of you ever worked with right triangles before, even in this class? So if I work with right triangles, when you've worked with right triangles before, what do we call that side? Hypotenuse. It's always what part of the triangle? Isn't it the longest side? Isn't it opposite the largest angle of that triangle? So the relationship between the size of the angle and the length of the side is very, very closely related. And you guys probably naturally saw it. Bigger the angle, bigger the side. Smaller the angle, what? Smaller the side. Pretty easy to do. So now let's think about that, how that can carry in a lot of different ways with triangles. Now the first one is a corollary to the triangle exterior angle theorem. Okay, let's just do a quick review. Do not read this theorem. If I have the triangle exterior angle theorem, remember we had here 3, 2, and 1. What's so special about angle 2 and angle 3? What are those called? The remote interiors, correct? They add up to the what? So we knew the measure of angle 2 plus the measure of angle 3 was equal to the measure of angle 1. Now, a corollary means it's closely related, right? So look what this says, and I think you guys are going to go, yes, common sense. It says the measure of the exterior angle of a triangle is greater than the measure of each of its remote interior angles. Well, yeah. Shouldn't the whole be bigger than one of its parts? Correct? So very kind of common sense. If it takes 2 of them to add up to the measure of that one, the larger one should be bigger. So it's using the idea here that angle 1 be greater than angle 2 or angle 3. A very kind of common sense thing. But don't you think that that's why it's a corollary? Like, well, of course I should be able to write inequality off of that. But now the next one, I actually name these a little bit differently than what the book does. The book just gives numbers for it, but I actually have a theorem. Guys, how many of you know the story of Goldilocks and the 3 bears? Okay, now humor me for a moment and you'll see where this is going, okay? Some of you are like, I'm worried. You should be. Okay, so Goldilocks and 3 bears. So Goldilocks is this girl who was getting lost in the woods, probably went where her mother told her not to go. And she gets a little scared. And she goes and knocks on this house. Now, again, in reality, this doesn't work for me that bears have a house. But anyway, going on. But remember the bears, Mama Bear was making breakfast, but it wasn't ready yet. And so the family of Papa, Mama, and Baby Bear went out for a walk. And then Goldilocks knocks on the door. Now, don't know what really worked with Goldilocks, but normally if no one answers, you go away. What does Goldilocks do? She just kind of walks in. So she trespassed. All right, so then, or breaking and entering, I'm not sure what you want to call it, but that's what she does. So then she goes in and
she sits there and she goes, she smells something really, really good, right? But remember, she's like tired. So what does she do first? She tries the 3 different bears' chairs. Remember that? You have the Papa Bear chair. Well, Papa Bear is a big bear, right? So he has the big chair and it's too hard. The Mama Bear chair is the middle-sized chair, right? And it's too soft. And then she goes to the small one, the Baby Bear chair, and it's just right, correct? And then it breaks. You know how that goes. Then she's hungry and she smells the porridge that Mama Bear made. And there's the big bowl goes with what Papa Bear, but it's too hot. Mama Bear has the medium-sized bowl, and this is where physics and temperature doesn't work. But Mama Bear's bowl is medium-sized and it's too cold. But somehow the smallest bowl, which should have been the freezing by this time, right, is just right. But again, it was 3 different sizes based off of the 3 different sizes of the bears, right? And then what does she do? She steals by eating the baby's food. Are you with me on that? So, and then, she gets tired. Again, wouldn't a normal child at this point in their life be worried that their parents would be looking for them? Probably already have their parents' iPhone detecting where they're at, correct? But no, Goldilocks decides now's the time to take a nap. And she goes into the bedroom, right? And this is, a nice, politically correct, very nice. There's 3 beds for 3 bears. The really big one for Papa Bear, and it's too hard. Then you go the medium-sized one for Mama Bear, it's too soft. And then you have the one that's perfectly sized for Baby Bear and Goldilocks, and it's just right, correct? And then somehow she doesn't wake up, and then 3 scary bears walk into the house, right? Who, I'm still trying to figure out, are they walking? Are they going forwards? But anyway, so she's there, and then they find her. Are you guys starting to see where this, I used to like this story as a kid, so I'm not sure anymore. But so basically they find the person still in their home that had already broken, entering, trespassed, and stole food and vandalized things by breaking the chair. And then she wakes up and she runs away, right? Now, what in the world does that have to do with geometry? What's so special about the 3 bears? There are 3 different sizes, correct? How many sides does a triangle have? 3 sides. How many different angles? 3. So does the size of the side and its opposite angle make a difference on the size of the angle? Isn't that what you guys just told me earlier? And the side length? So bigger the angle, bigger the what? Side. So basically if you have a Papa Bear angle, like that 90-degree angle that you had over there, isn't the side opposite going to be the Papa Bear side and be the biggest side? Are you starting to see? It's a little cheesy, but it really works. So guess what we're going to name this theorem? 3 Bears theorem. Goldilocks makes me mad. I'm not giving her credit, okay? But we're going to do 3 bears. I really have, to be honest with you. I think I give the political correct version of that now, but as a kid, it was great, oh, Goldilocks runs away, they didn't eat her, it's beautiful, and the bears don't do anything. It's the nice Christian approach, I guess. But me, I'm just thinking, no, you went into my house. All right, anyway. Now, let's write the theorem down, though, and you'll see exactly how this works. It says the following. Now, I'm only talking about 2 sides because you only need to talk about 2 sides at a time, but it really does affect all 3 sides. If 2 sides of a triangle are not congruent. So that means we already know that one side is going to be bigger than the other. Then the larger angle is opposite the longer side. All right. So this is basically what they're saying. If I talk about or compare side lengths, so like here in the hypothesis, it says segment AV is greater than segment BC. I'm just making these numbers off the top of my head to make some sense here, guys. So let's say this one's 10, that one's 8. If segment AB is length 10, what angle has to be the larger angle measurement? Right? And it's really, you can see it like here's the 2 sides. Bigger the side, bigger the angle. Smaller side, smaller the angle. It's really easy to see. So then you can make sure there's a comparison. That means, all right, so the smaller side, segment BC, is going to be opposite the smaller angle. Well, I can just naturally get a conclusion that the angles are going to be the same case. Now, what if I knew the 3rd side's measurement? Could I actually compare all 3 angles then? Yeah. So the fact is, It's really kind of common sense, as long as you know your opposite angles and stuff. Now, what's the next one? This is just going the opposite way. This is the converse of the three bears theorem. Now, understand, I think I'm the only teacher, except for maybe Mrs. Prempus, whoever calls it the three bears theorem. So if you ever go up to anyone, they have to be my former student for them to understand at all what you're talking about. Just remember, the three bears means three sides. If I compare the sides of a triangle, I should be able to get an idea which angles are bigger or not. And then converse goes the other way around. I'm going to compare the angles, and you should be able to tell me which sides are bigger as a result. Yes, ma'am?
Do you want us to use three bear theorem?
Totally could. Totally. Because since I told you, you may totally use that as your reference. The thing is, you just have to make sure it's clear what you're using it for. So on this one, the converse, we talk about angles first. So it's the following. If two angles of a triangle are not congruent, then the longer side is opposite the larger angle. So this time, instead, I'm talking angles, and then you're going to be able to compare sides. So makes it here like if this was, let's say, 100 degrees, this was 40 degrees. Obviously, segment XY should be the longer segment. And then we should have segment XZ would be the smaller one. It's just basing it off the side. Do you see how it's really common sense? Like if you draw it that way, you're going to see how it works. But here's how I've used three bears theorems and the converse of three bears theorem before in the past. I've actually asked you to describe it in your own words. Now, this is okay, their theorem, but I want you to really be able to explain to me in more detail than this, because I tell you it's three bears. So really, could you say something like, if there's three sides of a triangle and I know all three side lengths, I should be able to tell you which angle is bigger, which angle is smaller, based off of those side lengths. Isn't that a great description of the three bears theorem without it being so technical? But like, being able to use your words. Now the converse, if I know the measures of the three angles of a triangle, should I be able to tell by length which sides, by the angle measurements, which side's longer, shorter, or medium size, right? Or how about even being congruent? Think about your isosceles triangle theorem. If two angles are the same, what do you know about the sides opposite them? They're the same. Really, it's using this idea, right? Yes, ma'am.
So for the three bears theorem, not the converse, but like the original one, if you were to have, do you have to have a standing triangle for it to work?
It still works. You can have an isosceles triangle. The fact is, as long as you know if a side is longer than another one, I know the angle is going to be different measurements, and I should know which one it is. So like, here's where it's fun. This one is scaling, but this is fun. I said, write the angles in order from smallest to largest. I've been known on quizzes to make sure your reading directions, change it from largest to smallest. Hint, hint. I've been known to do that just to make sure you do the R word, read. But guys, think about how easy this is. Literally go smallest. So sit there and look. Okay, this is going to be a joke, but where's the baby bear side? Where's the smallest side? It's going to be 17.2. So the moment you do that, notice what did I just draw my arrow to do? Go to my opposite angle. So what's the smallest angle? Yeah, so I got angle F. Notice I'm not talking about measurements with it. I'm just saying, hey, I'm listing them. That's all they asked me to do. So I'm going angle F. Guys, where's mama bear side? Where's the middle side? So what's going to be your next angle? Angle H. And then what do I know here? That our papa bear side, 20.4, that means angle G is going to be the, like, is that hard? No, as long as you understand the common sense behind it. All right. Now, you guys do this one real quick. It says list the angles in order from the smallest to largest on triangle DF, where DE is 15, EF is 18, and DF is 5. You guys do it on your own. You should be done by now. If you would have done something the moment you read it, draw the what? Draw the triangle and then label the different parts, okay? Because I know the length of segment DE is 15, EF is 18, DF is 5. And I want to go from smallest to largest. That means I have to start with the baby bear side, right? So if that's the case, that's DF. Notice I didn't draw my triangle to scale, but I'm trusting my numbers. So if DF is the smallest, what's your smallest angle? Angle E, right? Well, what's our middle one? What's the mama bear one? DE, right? What's the middle-sized angle then? So it's going to be angle F. And then obviously you can leave your last triangle on there. Now here's the other way you could think about it. If I know the length of the segments, isn't the angle opposite the one that's not making that segment? So right away, if I knew that EF is the longest segment, what's the only vertex that can be opposite of it? D. So that's why I knew angle D was last. So it's another way you could look at those. It's still a visual thing you kind of think in your head, but isn't that just easy to draw it out? All right. Now, let's switch it around. Let's use the converse. It says, write the sides in order from shortest to longest. What would you guys do first on this one? You want to sit there and find out what the other angle is, right? All right, guys, so what's the measure of angle R, just to make sure that we're careful with this one? I heard someone say it. What is it?
40.
Awesome. So you guys got to be 48 degrees, is that right? All right, the moment you do that, isn't it quick to name your sides? And remember, I'm just listing them, so it just says write the sides in order. So if that's the case, guys, what's your shortest side? Yep, PQ or QP, doesn't matter which one you say first, as long as you have your segment bar there. What's going to be our middle side? And what would be our longest side? PR. Guys, what do you think? Now, this is what's scary. This is why the three bears theorem works. It's all about the size, like mama, papa, and baby bear size, right? It's all about the size of the sides and its opposite angles. Same type of concept, just in a weird way. All right, list the sides in order from shortest to longest. Those of you who are visual, what are you going to do? Draw it, of course. Always draw it. All right, guys, what's my shortest side? EF, all right, so segment EF. Make sure I can get it written down here. Segment EF, awesome. What's your middle side? DE. And what's your longest? Should be EF, right? Oops, longest should be DF. Hello, I did the wrong one. Why did I do longest that way? Hello. Need to look what I write down. Longest. And be DF. Does it make sense? Now, someone asked, what if the sides are the same? Well, think about it. It's not counteracting what this theorem is saying. Because what if I had something that looked like this? This is 70, 70. Guys, what's the other angle? What would it be? Shouldn't it be 40? Okay, now think about this. I have DOG. We have triangle dog here, okay? If that's the case, I'm not going to ask you to list the sides from smallest to largest, but would I be able to say, okay, what's the smallest side of that triangle? And you'd tell me the what? DG, which is the base of that isosceles triangle. And doesn't it make sense if they're different sizes, you should have different measures of lengths, but if I have the same angle measurement, shouldn't the opposite sides be equal, like our isosceles triangle theorem told us? So notice they really complement each other as theorems. So that's a lot of the stuff that kind of common sense. So now think about why a scaling triangle is kind of important now, or knowing the measures of angles on triangles, because that can affect the side length opposite of it. So it's a big deal. All right, now the next part, what I'm going to get you is actually very helpful for standardized tests. It's used a lot. It also helps you to see if people are having common sense ideas. But let's think about it for a moment. And we know, and this is, I know this is a Doug Gregerson moment, that three line segments make a triangle, right? Three that they share, their vertices, they only share two segments at a side, they're gonna work. But here's the thing, can I just give you any three segments and will they work? No, because here, obviously if I had 1, 4, and 4, and 7, that made a nice triangle. But what happens if I make these two sides here 3 and 3? Are they gonna be able to intersect and make a triangle? No, in fact, they'd fall down right here and there'd be a nice little gap of about a unit of 1. So it doesn't work. So what if I actually did something like this? What if I had the fact that this is 6? Can I have this one of 3 and this one of 3? Will they make a triangle?
Would those three segments, 3, 3, and 6, make a triangle? Why not? Yeah, she's like me, she's visual. This is how I tell her every time. Katie, you're totally right. She goes, it's gonna fall down. Because if I'm gonna make those so that they intersect, so that these two intersect, what's gonna happen, guys? Where are they gonna end up intersecting at? Aren't they gonna end up intersecting right here in the middle? Okay, did that make a triangle then? All right, so what has to happen in order to make it a triangle? What? Yeah, something has to be bigger, right? Could I go 3.1 and then all of a sudden does that make a triangle? So basically, I think what you guys are getting at, and I think you're going to get with me, is like two of the sides, any two sides, have to add up to be bigger than the what? The third side. So any two sides have to be greater than the third side. If not, you do the collapse thing, or have a big gap thing when you're working with your triangle. So you have to be very careful. Now that's given, it's called the triangle inequality theorem. Okay, and so this is what it says, but obviously I love the conclusion because it basically shows you have three scenarios you have to consider when you're doing this. But the triangle inequality theorem says the following: the sum of any two side lengths of a triangle is greater than the third side length. So the sum of any two side lengths of a triangle is greater than the third side length. Yes? But does it still follow the rules? Let's see. Say 3, 3, and 3, right? If I take any two sides, is it still bigger than my third side? So it follows it. See how it works? It still will work. It just only throws out it. But yeah, it works. Yeah, so long as any two sides are bigger than the third side, do you have a triangle you can draw or make? Yes, ma'am. Right, because 1 plus 2 is not greater than, yeah. So if I had sides 1, 2, and 3, let's say side lengths is probably what I should say, better notation. Will that make a triangle? Based off of this theorem, it can't, and what we played with earlier, because 1 plus 2 is not greater than 3. It has to be greater than, or it'll do that collapse in on itself thing. Does that kind of make common sense? Okay, now here, guys, here's where it gets a little more fun now. Because of this, I now can find a range for my third side. Let's just say I only gave you two sides. So here I have a triangle, unless I said this is 10 and this is 4. What would be possible lengths for my third side? What does the third side have to be smaller than? Here's my third side. What are possible lengths for this? Yeah, Connor. All right, you mean the third side has to be smaller than 14. Oh. Yeah, it has to be smaller. So it has to be less than the sum. So the third side, it's going to be less than 14 because I know 10 plus 4 is 14. And remember, any two sides have to add to be greater than the third one. So I'm just writing it in opposite order, inequalities direction sign. But what would it have to be bigger than? 6. How did you guys get that? 6 plus 4. Someone goes, 6 plus 4. Well, yeah, exactly. Don't these two sides have to add to be greater than 10? So it has to be larger than what? It could be 6.00000001 and work, right? But it has to be greater than 6. So isn't that just the difference of those two? So my third side can anywhere be between 6 and 14, but neither one. So that actually gives a range, and this is the term that we use. We use that inequality right there. The difference of the two sides and the sum of the two sides. And we just make a compound inequality that describes it. It gives a range of what are possible answers. Those are like questions SAT, ACT just love on this. So you have to make sure you really have these down. All right, so with this one, let's have a little bit of fun. Now,
Notice no triangle drawn. You don't need to draw a triangle. You need to be able to use your triangle inequality theorem. It says, tell whether a triangle can have sides with the given lengths. Explain. Now, notice what I wrote in parentheses here. I need to see your what? I need to actually see your explanations on your homework or I don't give credit. You guys remember that? It's called the complete directions. A lot of you don't like, when it says explain, that seems to be the part that's forgotten a lot of times on homeworks. But here we have 7, 10, and 19. Is that those three segments, will they make a triangle? All right, yes or no? What's your guys' answer? All right, and so here, you'd say no, and then you tell me why. Because, and this is where you can keep your math very easy to do it. Because what? 7 plus 10 is what? Is not greater than what? If you want to do a little more math way of showing that, can you go 7 plus 10 is not greater than 19? Just do it that way, symbols only. I'd take it either way. Because two sides didn't add up to be greater than the third. You just have to show one oops. Remember, one counterexample and you win. So 7 plus 10 is not greater than 19. So no. So I would long say no because either do this top one or the middle one would be great explanation for me. Nothing fancier than that. How about the next one? I got 2.3, 3.1, and 4.6. Guys, don't put your stuff right away. You can give me a couple minutes even if after the bell rings. What happens next? Is it yes or no? Yes. Yes, and that's all you have to say. Yes, because the sum of any two side lengths, don't put your stuff away, we're still taking notes, of any two side lengths is greater than the third. Basically, are we repeating what we know about the triangle inequality theorem? Now, you could show me all three pairs doing that, but I think this is the easiest way of doing it. All right, now, here's where you guys need to think about. This is where I went and talked to you about it earlier, so this should be very quick. It says the length of two sides of a triangle are 8 inches and 13 inches. Describe the possible lengths of the third side. Guys, what would you do? This got one's 13, which is 8. This is my third side. How would you describe it? Perfect. And just show me a little bit of work and you're going to be good. So guys, think about your third side. If you did it like this, show me what you added together and show me your difference. Are you guys with me on that? So that's your way of describing possible lengths. The third side is going to be between those. Are we good with that? Yes. All right. Go have a great day. I will see you in chapel.